This video deals with equilibrium. Now there are two conditions for equilibrium. We'll see the second one later. But the first condition is that the sum of the forces must be equal to zero. Or more specifically, the sum of the forces in the x direction have to be zero, and the sum of the forces in the y direction have to be zero. So let's go through a problem here. We want to calculate the tension on the wires supporting the 70-kilogram boy. Here's the boy. Here's the wires, TL and TR. We want to determine the tension on those. Notice that angle here and here is 5 degrees, and his weight is acting down. Okay, so the steps in solving the problem is to construct a table that has the x and y components of TL and the x and y components of TR and the x and y components of W. Then we want to set the sum of the x and y components to zero, because that's the condition for equilibrium. If it's in equilibrium, this has got to be true. And then we solve for TL and TR. So this is a free body diagram that shows the forces on that picture we saw on the previous slide. Here is TR, here is TL. There was a vertical support here, and there was an angle of 5 degrees here, but geometrically alternate interior angles would mean that this angle is 5 and this angle is 5. Okay, so we start out by computing x and y components. We'll do TL first. The cosine of 5 degrees equals TLX over TL. TLX is going to be this direction. It's adjacent to this 5-degree angle, so that's why we're using cosine. We solve for TLX. TLX is equal to minus 0.99 TL. Notice that it's minus because that x component is acting to the left. Okay, now we do the y component of TL. This time it's going to be sine because the y component is opposite the 5-degree angle. So sine of 5 is equal to TLY divided by TL. This time TLY is 0.087 TL. And that one is positive because that y component is acting upward. Okay, so now we go to the right, TR. Cosine of 5 degrees equals TRX over TR. TRX is equal to 0.99 TR. In this case, it's positive because it's acting to the right. And then the y component of TR is going to be sine of 5 degrees equals TRY over TR. So TRY is also equal to 0.087 TR. Again, that one is also upward, so it's positive. Now we go to the weight here. Since it's acting vertically downward, the x component is 0. The y component is the magnitude of the weight. Remember, we've got to use weight here, not mass. So that's going to be 9.8 times 70 is mass, and it's negative because that's acting along the y-axis in the downward direction, so that is negative 686 newtons. Here is the table, and I filled in all of the components that we calculated in the last slide. There's TL, the x and y, TR, its x and y, W, its x and y, and then the sum. Remember, that must be 0 if the system is in equilibrium. Okay, so we take this, we sum these, and set them to 0. So we have 0.99 TL plus 0.99 TR plus 0 equals 0. And then that means that 0.99 TL equals 0.99 TR, or TL equals TR. And that makes sense if you look back on that picture on the previous slide. The boy was standing right in the middle of the cable, so it would make sense that there would be equal tension on each side. Okay, so now we sum the y components. So we have 0.087 TL plus 0.087 TR minus 686 newtons equals 0, or 0.087 TL plus 0.087 TR equals 686. But since TL and TR are equal to each other, we can just substitute in TL for TR. So now we have 0.087 TL plus 0.087 TL equals 686 newtons. Now we can solve for TL. TL is 3,900 newtons, but recalling that TL is equal to TR, then TR is also 3,900 newtons. The second condition for equilibrium is that the sum of the torques must be equal to 0. And that means that the sum of the torques in the clockwise direction have to be equal to the sum of the torques in the counterclockwise direction. And remember that torque is equal to force times the distance from the point of rotation. So if we look at the two children here on the seesaw, we see that the weight of this child is going to cause a torque that's going to cause the seesaw to rotate around this way, counterclockwise. And this child's weight is going to cause the seesaw to rotate around this way, clockwise. And for the system to be in equilibrium, that torque and that torque must be equal. Okay, so here is an example. We've got a 25 kilogram boy, sits 4 meters from the fulcrum. There's the fulcrum right there. On a seesaw, find the distance from the fulcrum his older sister must sit if her mass is 30 kilograms. So we set this up by noting that the sum of the torques in the clockwise must be equal to the sum of the torques in the counterclockwise. So that means that this child's weight, which is 25 kilograms times 9.8 times his distance from the fulcrum, the point of rotation, which is 4 meters, must be equal to this child's weight right here, 30 kilograms times 9.8 times her distance from the fulcrum, which is R2. So we just take this equation here and we solve it for R2. Notice that the 9.8s here will cancel out, and so we end up with 3.33 meters would be the distance that she must sit from the fulcrum. By the way, the first condition for equilibrium also holds in this, because this force, this upward normal force on the tip of the fulcrum, must be equal to the weights of the downward forces, which is the weights of these two children. Here's a problem that uses both the first and the second condition for equilibrium. So we've got a 20 kilogram beam that's 10 meters long, and it's got a mass of 50 kilograms right here, 2 meters from the right end. So this is 2 meters here. So this obviously is 8 meters. We want to calculate the force exerted by each of the supports. So the support here and the support here would provide an upward force. By the way, notice that the weight of the beam is going to be one of the forces involved in this problem, and that's considered to act at what's called the center of mass. And the center of mass is the point where all of the mass is can be considered to be acting. And as long as this is a uniform beam, that would mean that the center of mass acts exactly in the center of the beam itself. All right, now remember that we're going to need both conditions for equilibrium to solve this. So we start out with the first condition of equilibrium, which says that the sum of the forces are equal to 0. Now, we said previously that the sum of the forces in the x direction and some of the forces in the y direction have to be 0. But in this particular case, there are no forces in the x direction. It's only in the y direction. So that would mean that F1 plus F2, these are the two upward forces, minus the weight of the beam, which is 20 kilograms times 9.8, minus the weight of the block, which is 50 kilograms times 9.8, equals 0. Or the up forces equal the down forces. So the two up forces, which are F1 plus F2, is equal to the sum of these two, which is 686 newtons. Okay, now, we can't solve this, right, because we have two unknowns here. So now we have the second condition for equilibrium, and that is that the sum of the torques in the clockwise direction is equal to the sum of the torques in the counterclockwise direction. Okay, now we don't really have a natural point of rotation here like we did in the seesaw problem. So the good news is we can assign it to be any place. So if we assign it to be right there at F1, that will eliminate one of these torques from the problem, make it easier to solve. So that's what we'll do. Put the point of rotation right here. Okay, so F2, therefore, if this was the point of rotation, this would cause the system to rotate counterclockwise. So we can say that F2 times this distance, 10 meters, okay? Now these two forces would cause the system to rotate clockwise. So they would be 20 kilograms, the weight of the beam, times 9.8. Now remember, this is acting at the center, so this distance is 5 meters, plus this weight, which is 50 kilograms times 9.8, times this distance, which is 8 meters. So now all we have to do is solve for F2, and F2 comes out to be 490 newtons. And since the first condition, the first equation from the first condition of equilibrium, said that F1 plus F2 is 686 newtons, now we can solve for F1 simply by subtracting F2 from the 686. So there we have it down here, and F1 is 196 newtons. So now we're going to take a look at three types of equilibrium. First type is stable equilibrium. So this would be when an object is displaced, a force or a torque acts to bring the object back to its equilibrium position. So, for example, if you had a heavy refrigerator and you tipped it up very slightly and then let it go, it's going to come back to its equilibrium position. It's going to go back to its original position where it was resting on all four of its supports. Unstable equilibrium is when an object is displaced, a force or a torque acts in the same direction as the displacement, and that results in bringing it further from its equilibrium position. So this diagram right here shows a pencil balanced right on its tip. I think that would take a lot of patience to do that, but if you could do it. Notice this CG here stands for the center of gravity. Same point as the center of mass, but the only difference is it's at the point where all the weight of the object is considered to be acting. So at this point, the center of gravity is exactly over that pivot point. Now, if you take this and displace it ever so slightly from its equilibrium position, the torque exerted by the center of gravity is going to cause the pencil to topple over. Okay, so the last one is neutral equilibrium, and here equilibrium is independent of its displacement from the equilibrium position. So if you have a marble resting on the floor, you displace it slightly, the marble moves to the right here a little bit, its displacement is now changed from its original position, but yet it's still in equilibrium. So the equilibrium position is independent of its displacement from the original position.